Next up, we have a talk on parallel sorting library and algorithm for massively parallel machines. The speaker is Vipul Harsh. He's a master's student at the Parallel Programming Laboratory at UIUC. So over to Vipul.
Thanks, Nitin. My name is Vipul Harsh, and I am a graduate student here at PPL, working with Professor Kale. I'm not going to be talking about the runtime system or any application side applications today. I'm going to talk about a very important problem that's quite frequently used in HPC applications. So this is our work on work and findings on parallel sorting. So we care about parallel sorting a lot for HPC applications because we have massively parallel scientific applications like Changa, which you heard about today earlier, that uses parallel sorting very frequently in its computation. And here is another cosmology code which also uses sorting for better load balance and locality. So that's why we want really very performance, a sorting library that really performs well. So before I proceed, I just want to outline a high level list of goals that we want from a sorting algorithm. And first we want a very good load balance across processors. So after the sorting algorithm finishes and after the redistribution of data, every processor should roughly have the same amount of data, and this is also related to the performance of applications, because if there is load imbalance, then for any subsequent computation you do, your application will slow down. We also want optimal data movement because the data could be massive, and you don't want to move the data more than once, and this is even more true for big data applications which have massive amount of data. Third, we want our algorithm to be robust to all sort of input distributions. It should handle duplicates and should not assume much about the underlying distribution. And of course, we want scalability and performance. So here is a basic template that's really at the core of almost all of the parallel sorting algorithms that we have that's used for very highly parallel applications. So there are P processors, and there are n over P keys in each processor. And the high level goal is that you determine P minus 1 splitter keys to partition the entire input into P buckets, and you assign each bucket to a processor, and depending on which bucket a key falls in, it goes on to that processor, and that's parallel sorting. And really all the algorithms out there are sort of have this at the core. So sample sort is one of the early algorithms that's quite frequently used. So at the heart of sample sort is every processor just picks some number of keys from its input, and it assembles all the samples at one place at a root processor, and a root processor just looks at all the samples and picks P minus 1 splitter keys. And so the problem with sample sort is it really needs a lot of samples if you want good load balance, and that sort of prohibits sample sort to be used in really massive applications. So for example, if you have a really if you have a big problem size like 100,000 processors, and your threshold for maximum load imbalance is about 5%, then you need about 8 GB of sample size, which is quite a lot. So another popular parallel sorting algorithm is histogram sort, and it's quite popular. So the basic idea is that you pick some number of candidate keys and compute the rank of each candidate key, and this is done using a global histogram reduction, and that's where the name comes from. And once you know the rank of each candidate key, you can select splitters from the candidates, or alternatively, if you are not happy with the splitters, you can refine your candidates and then repeat these steps. And histogram sort refines these candidates using an extrapolation technique. So it works quite well for large P. In fact, I think it's used in Changa. But it can take more iterations if the input is skewed. So there are no guarantees on the number of iterations, but usually it's not large. It works quite well. So histogram sort with sampling is our take on the problem. It's an adaptation of histogram sort, and the basic difference is that before each histogramming round we sample to find the candidate keys, and the idea is that we sample intelligently, we using results from the previous rounds, and we don't sample keys that we know are wasteful, that's not relevant to the problem. So that's intelligent sampling, and we will show that HSS is histogram sort with sampling. So HSS has very sound theoretical guarantees. Those guarantees are independent of input distribution. So you can it will run on anything with the same guarantee, and in a way it also justifies why histogram sort does so well, and that's because the extrapolation technique in histogram sort, you can think of it to be same as sampling. For example, if the input were a uniform distribution, then the extrapolation technique will be perfect. So even if it's not so uniform, but there is some degree of uniformity in the input, histogram sort does quite well. So I'll describe the intelligent sampling technique in HSS, and so to remind you, the high level goal is to pick p-1 splitter keys to partition the input into P ranges. So ideally we want our splitters to be evenly spaced so that all processes are perfectly load balanced after the sorting algorithm. So the splitters are spaced n over P from each other ideally. And after the first round, we will know of some splitters that are somewhere that are all over the place, and the key idea is that for subsequent rounds of sampling, you only need to sample from these shaded regions, and the observation is that if you have a sample that's outside a shaded interval, then that's wasteful, and that's because you already know a key that's closer to the ideal splitter key. So you would always pick a key that's closer to the ideal splitter rather than picking a key that's further away. So that's how you sample intelligently. And really, one of the main contributions that we have was to characterize HSS theoretically, and there were some very interesting results. And one of our main results was that if you have a load imbalance threshold of epsilon, then with k rounds of histogramming you need that many samples, and in fact that comes out to be much less than sample sort. So that's the theorem. These are the sample sizes for sample sort and histogram sort. I'll go through them very quickly. So this is p log n over epsilon square. That's quite large, in fact. With just one round of histogramming, you reduce it by a factor of epsilon. So if epsilon is, let's say, 5%, then that's about 20x. In general, with k rounds, you have this complexity, and if you optimize for the number of rounds, this is the optimal number of samples that you can get. So in comparison, this is the difference between the number of samples between HSS and sample sort. And this is just a graphical representation of the same thing. The 350x factor that you see is the reduction in sample size between sample sort and HSS, and this is just a graphical representation of this table. So we experimented with number of histogram rounds to see to confirm what we saw with our theoretical results, and we kept the sample size of about 5 from each processor. So every processor just picks 5 keys from its input data. And we observe that the number of rounds never really changes with increasing p, and that's sort of expected because the number of rounds that the theoretical analysis says is of log p complexity, and that hardly ever increases. So that's why you see constant data in the table. So another thing that we did, we wanted to optimize for shared memory, and the reason was that most modern machines now have massive within node parallelism that you can exploit. So for example, the Blue Gene Q machine you can run 64 hardware threads on one node. In the new Stampede machine, you can run more than 250 hardware threads on one node. And so the challenge is how to take advantage of this massive within node parallelism. So we go back to the algorithm and we find that after you determine the splitters, each processor has to send a message to every other processor. And that's the message that contains all keys that are destined for that processor. So there are about p square messages in the network, and since there are so many messages, all your messages are very fine grained. And that sort of is an overhead if your p is large. And a simple optimization is if your all messages that have the same source physical node and the same source destination node, if you combine all such messages into one, so you have only one message going from one node to another, that will give you about order n square messages. And if you think that the number of nodes is about 10 times less than the number of cores, then that's about 2 orders of magnitude less. So what about splitting? If you use the previous optimization, you will realize that we only need splitting across nodes. And that's because if you look at a key, you only need to figure out which node to send it to and not which core to send it to or which PE to send it to. You really need to find which node to send it to. And so you need only n-1 splitters, and that further reduces the sample size by an order of magnitude. So it really the splitter determination phase is really small now. But of course, once you send data to a destination node, once it receives all the data, it will have to redistribute its data among its local cores. So there's an extra complexity of adding a final within node sorting after this data exchange. So after doing all this, this is a weak scaling experiment that was run on Blue Gene Q, and we found out that after doing all this, the histogramming step really takes a very small fraction of the running time. So that is the part that's marked in red, and most of the time is spent in local sorting and the data exchange. And so both local sorting and data exchange are sort of inherent to any algorithm, because you would have to locally sort the data and you would have to move the data. There's no other way. So it's really unavoidable cost. So in conclusion, HSS combines sampling and histogramming to accomplish fast splitter determination, and so in a way it's best of both sample sort and histogram sort. It has very sound theoretical guarantees, and that's an important contribution of our work. And from our experiments, we realized that most of the running time is spent in local sorting and data exchange, which is sort of unavoidable costs in any algorithm. Future work, we would ideally want to integrate it in HPC applications, and hopefully if we are able to demonstrate performance improvements. So that's it. Thank you.
Any questions?
So have you done a direct comparison with the sorting algorithm in Changa,
Right.
with the HSS with one of the benchmark data sets?
So you mean histogram sort with histogram? So the one used in Changa, I think, is histogram sort.
Right.
So we do. I didn't have. So I think the question is, what is the improvement of HSS as compared to histogram sort?
As
Or
implemented,
the data set used in Changa.
yeah, for one of the
Oh,
Changa
so
data sets.
I don't have numbers for that yet. I don't have numbers for that yet.
And in fact, I'm thinking about Changa. There is a couple of.
So the thing is, the algorithm used in HSS is really independent of the input distribution. So no matter what input you have, it will have the same number of rounds. But histogram sort might take a larger number of rounds if your input is skewed and so on. So I mean, there is an edge that histogram sort with sampling has with skewed distributions.
There's a couple of other twists there. One is that that node level thing may not work or may have to be modified because we want to partition into chars. And number two, you might want to combine load balancing with this by giving each particle a load. That might be a.
I mean, you can still do something. You can still combine all messages that are going to the same node, but you still do a char level splitting, but still has some benefit.
So how do you decide how many sampling rounds to do with your algorithm?
Yeah, that's a good question. So so the way we do it, the way you're going to do it in a practical implementation is you decide how many samples to take each round, and you keep doing that until you get satisfactory splitters. The guarantee is that it will not take too many rounds. It will take 3 or 4 rounds or something like that.
So you have a theoretical bound on the number of rounds?
Yeah, that's
Okay.
right. Yeah.
All right. Thank you.
Any more questions? Let's thank Vipul for the talk.